Welcome to Chemistry 112. Today is the test, so let's make sure we come and take that. Keep in mind, if you can't make it to 7 is inconvenient. You can find me today, typically in my office, 11 to 1, possibly near the lab, 11 to 1, or in the lab, 1 to 3. If you're not currently doing lab this week, or if you want to do your lab next week, you could go do it in lab. If you cannot make it tonight and you cannot make it today at all, best come take it on Friday. You don't really have a good excuse, is the fact that I've had the test ready all week. So, don't be like, well, my car broke down last night and then I don't have any time for it to make time. Remember, you can have a page, front, back, whatever you want on it. You don't need Ka. What was the question? Chapter 16 and 17, yes. So it's on the acid base and the complicated acid base equilibrium, which includes buffers, titrations, and KSP. But so you won't need Ka values, you won't need KSP values, but maybe you want how to set up a KSP. Maybe you want how to set up a Ka. Whatever you feel you need on there. But like any constant that you may need for the math will be given. You should be able to solve most of the things with the information given. We briefly talked about entropy and spontaneity. Entropy being the randomness of the universe, and spontaneity being whether a reaction will happen without any outside force, and stating that the second law of thermodynamics states that any spontaneous process will increase the entropy of the universe. We talked about how we could calculate delta S for a system by just looking at the values of a chemical reaction. But we just introduced right here that to find the delta S of the surroundings, we can look at the heat of the system. In fact, the inverse of the heat of the system, because heat lost by the system is heat gained by the surroundings. But because it's done isothermally, we have to account for what is the current temperature of the surroundings. So hotter surroundings means lesser change. Cooler surroundings means change. So let's apply that to a problem. Okay. So here is a thing we actually just did. We talked about KSP expressions, which dealt with precipitation reactions. And in fact, that's what I'm teaching in General Chemistry 1 right about now. We're just finishing up precipitation reactions and all that stuff. So this reaction, we know this reaction happens. You put silver nitrate and sodium chloride, we form a solid. Now let's look at the values, Na and O3. Now conveniently, I calculated all these for us. So I'm going to write these down just so when I do the math, I don't have to be flipping back and forth. But so we have for delta H is negative 100.7 to 20.37. Let's see. Silver chloride is negative 127, 96.11. And NaNO3 is negative 446.2 and 207.0. And the last one, sodium chloride, is negative 407.1 and 115.1. Oh, 115.5. Okay. Now, pulling up cam of the dot cam to calculate this. To calculate delta S universe, we need both delta S system and delta S surroundings. To calculate delta S system, that's going to be the easy one. It's just going to be products minus reactants. So our products, silver chloride, 96.11, and sodium nitrate, to say it's 207.0, minus our reactants, silver nitrate, which was 220.35 or 3, I think it's 37, and sodium chloride, which was 115.5. So products minus reactants will give us the delta S of the system. That's right, minus 220.37 minus 15.5. If we just look at it by this, by the book, just by the entropy goes down. The entropy of the system goes down by a little bit, 32 joules. So obviously the entropy is not the driving force. It has to be the delta S surroundings for it to be spontaneous. So calculating the delta H, we're going to calculate the delta H. The delta H is just, once again, products minus reactants. Product 127. Product negative 446.2 minus the reactants negative 407.1 and negative 100.7. So keep in mind these are all negatives, so when you subtract a negative, it's the same as adding a positive. 0.2 plus 407.1 plus 100.7. So the delta H of the system, delta H is negative 65.4, and this is kilojoules per mole. Kilojoules per mole. Keep in mind, that one's in joules per mole Kelvin, and this is kilojoules per mole. I'm going to move over here real quick. To get the delta S surroundings, delta S surroundings is equal to negative delta H over T. Negative delta H over T, meaning, well, and we want them in the same units, meaning that when we say negative of a negative 65.4 kilojoules, we're probably going to want to times that by 1,000 joules per 1 kilojoule. And there's one other thing. What's the temperature? The temperature was 10 degrees Celsius. 10 degrees Celsius is what Kelvin? Why Kelvin? This is in joules per mole Kelvin. So this should be in Kelvin. So 273 plus 10 is 283 Kelvin. So we have positive 65,400 divided by 283. So the delta S surroundings is 231 joules per mole Kelvin. So the delta S of the universe, putting it both together, is, let's say, 231.10 minus 32.76. We have a net effect of 198.34 joules per mole Kelvin. So the entropy of the universe does indeed go up. Go up by a ton, but it does indeed go up. Let's see if it's easier to read or harder. Let's see. It does indeed go up. So in this case, the precipitation of silver chloride is not entropy driven, but enthalpy driven. When this happens, the solution warms up by a bit. And so this is spontaneous because of that this is exothermic. It makes the surrounding solution more random, even though the individually on the atomic level, it's less random. So but it's going to be a lot of this kind of thing. You take the numbers from a table, products minus reactants, multiplied by their coefficients. It just so happens that all the coefficients in this balanced chemical equation were 1. Because they were 1, we didn't have to do any tricks there. We did that. We calculated delta H. We calculated delta S. One key thing, when you add these guys together, you got to make sure the units are the same. You can't add joules per mole Kelvin to kilojoules. Well, you could, but you would find out your math is totally wrong. You're adding a big number to a small number, and suddenly, why is the number's not adding up? It's like I'm adding a milligram to a gram, and then suddenly, what? 5 milligrams to 10 grams. I'm wondering why my number isn't 15. Now, a mathematician by the name of J. Willard Gibbs proposed a new state function called Gibbs Free Energy. That's the event. Create a new function. You can name it after yourself. So you can live forever or be hated forever, depending on how you feel about this by the end of the year. But Gibbs Free Energy is a way to quantify the spontaneity of a reaction. It's really just a reiteration, a reformulation of the second law, that for a spontaneous reaction, entropy of the universe will increase. Well, Gibbs free energy is just a way of quantifying the spontaneity. So rearranging the original equation, we get delta G, which is a state function, is equal to delta H minus T delta S. So delta H is our enthalpy, T is our temperature in Kelvin, delta S is our entropy. You got them. Delta G is typically given in kilojoules per mole. S is typically given in joules per mole Kelvin, so you would have to convert. But it's just this statement will mathematically agree with the second law that whenever a reaction is spontaneous, the entropy of the universe will increase. But please note, due to how this is set up, when a reaction is spontaneous, delta G will be a negative number. Delta G is a negative number. When the reaction is non-spontaneous or won't work, delta G is a positive number. But remember, what is a state function? A state function has certain unique characteristics, meaning that it doesn't matter how we go about calculating this. We only need to know the initial starting point and the final starting point. We kind of dealt with this when we dealt with enthalpy, which was a state function. Entropy is also a state function. And so was K. The equilibrium constant K was also a state function. So we're going to be building on that. This is a state function. You can put multiple different reactions together and use that to calculate the overall spontaneity. But so in practice, when delta G is less than 0, it is spontaneous, and this is a forward-favored reaction. The reaction is going to go towards products. The larger the delta G value we have, the more spontaneous the reaction, essentially the more reactive it is. However, much like equilibrium constant K, delta G does not indicate the speed. Kinetics and thermodynamics are independent of each other. So we could have a reaction that goes incredibly slow or spontaneous reaction that goes incredibly fast, all things considered. Delta G greater than 0 would mean the reaction is what we call non-spontaneous. It would not proceed without work being done. But because of the state functionality of delta G, if a reaction is non-spontaneous in the forward direction, it would be spontaneous in the reverse. To go backwards from products to reactants would be spontaneous if delta G is positive. Because remember, with enthalpy, if the forward reaction produces heat, the reverse reaction absorbs the same amount of heat. Now, because of this, delta G of 0 has a special meaning. When delta G equals 0, neither the forward reaction or the reverse reaction is favored. That sounds like something we've previously talked before. When delta G is 0, this is achieving chemical equilibrium. When the reaction of forward and the reaction of reverse are neither favored nor disfavored, so the reaction essentially stops. It's not going to go towards products, but it's not going to go back towards reactants. When delta G is 0, we're at chemical equilibrium. Now, in a reaction, delta proceed from negative and approach 0. It's going to slowly increase until we get to 0. If it shoots past and goes to positive, then it would have to swing into reverse. But delta G is going to gradually approach 0 as a reaction goes forward. Now, we can calculate delta H and we can calculate delta G basically. I already have the work shown. That's my fault, but we'll work with this. We won't even bother to go with the doc cam in this case since the work's already shown. But as we see here, to calculate the delta G of the reaction of barium oxide with carbon dioxide forms barium carbonate. The first thing we'd have to do is calculate our delta H. Our delta H value would be products minus reactants. So our products is the product is barium carbonate, -1213. The reactants are barium oxide and carbon dioxide. So we'd add those two together and subtract them from 1213. So the total of the reactants are -393.5 and -548 is -941.5. So when I subtract that from 1213, I subtract a positive 9, well, I add a positive 941.5 the 1213, and I get -271.5, as you see here. I would do the same thing for products, for the entropy. I'd say products minus reactants. Products is 112. Reactants are 72.1 and 213.8. When I say products minus the reactants, I'd get negative 173.8. Now, the equation is delta H. The equation is delta H minus T delta S. And I have to make sure to convert this into joules to kilojoules, so that kilojoules and kilojoules can add together. So I have to divide this by 1,000. So the temperature is 25 degrees, so that means 25 plus 273 is 298. Our delta S, we can calculate that. We have to divide by 1,000, and then once we do that, we add those together. So while this is not entropically favored, because we go from a gas to a solid, it is enthalpically favored in that when you absorb the carbon dioxide onto the barium oxide, it produces a lot of heat. So will this reaction happen? We have a negative 219.7. The answer is yes. When you have a negative delta G, it is favored. I don't know why that. Now, please note, there's often a tiny little circle next to the delta G, delta H, and delta S. This has a special meaning. We may have seen this before, but I'm going to refer to it again. This is referred to the standard state, the standard free energy, the standard enthalpy, or the standard entropy. When these values are calculated, they're calculated under a standard set of conditions. If there is an element in there, we are going to use a pure solid or liquid in elemental form. If there is a gas, we're going to use 1 atmosphere of gas. If it is aqueous, we're going to use 1 molar aqueous. Because of the nature of the standard state, for delta H and delta G, pure elements will have a standard state energy of 0. Now, as we said, enthalpy had a standard state of 0 because how much energy does it take to make a pure element from a pure element? Well, it should be none because a pure element already exists. The same thing about spontaneity. What is the spontaneity of transferring the pure element into itself? Because of the definition of that, producing oxygen from oxygen should be a net zero process. You don't need to do anything to turn oxygen into itself. Because these are delta G and delta H, they will be 0 for pure elements, but entropy will not. But when calculating delta G standard, we will assume 25 degrees Celsius unless otherwise noted. So if I just say calculate delta G at standard state, we're going to assume 298 Kelvin. So with that in mind, it is possible to calculate the delta G of formation for a compound. Just use tabulated delta G value. You don't always have to go from delta H minus T delta S. You could use the delta G values and you could get the same number. They have the values tabulated up. However, if for whatever reason the temperature is not 298, then you cannot use those values. The tabulated delta G values will assume the temperature of 298. So, but just a quick value, calculate the delta G standard for the transition of carbon to graphite. Carbon to graphite. Real quick, carbon is 2.84, graphite is the standard state. 2.84 minus 0 is going to be, God, what did I do wrong? Oh, I did the other way around. Products minus reactants. Carbon to graphite. Carbon from diamond to carbon graphite would be 0 minus 2.84. So our delta H is actually negative 2.84 kilojoules per mole. Not very spontaneous, but interestingly enough, it is spontaneous. Diamond will degrade into graphite given enough time. However, once again, delta G is not necessarily related, is independent of kinetics. So we don't have to worry about our diamond rings degrading in our lifetime. It actually takes thousands of years. It takes thousands and thousands of years. It's a slow process. But the fact of the matter is, diamonds are less stable than graphite, and so will eventually degrade. Another back old Superman comic. I think Superman had to solve some war between an African tribe, and so a missing diamond. I think he picked up a piece of coal, crushed it in his hands, and used heat beams, laser beam eyes, to turn it into graphite, to turn it into a diamond, and then used it to replace the missing diamond. That would be an optimum example of pushing a non-spontaneous reaction to products. He put in outside work in order to force it against the system. Typically, entropy of the universe would decrease in that process. So you need to put in energy from an outside source to make it work. What did he do? He used high pressure and high heat, and he put in the energy to reverse this process. Now, because delta G equals delta H minus T delta S, spontaneity is temperature dependent. Temperature dependent. At high temperatures, entropy will have a greater influence. And at low temperatures, obviously, will have a lower influence. So we can imagine 4 different possible situations based on the signs of H and S. Temperature, remember, can never be negative. 0 Kelvin is as low as it goes. We can imagine 4 situations. If enthalpy is positive, heat is absorbed. If enthalpy is negative, heat is released. If entropy is positive, it becomes more random. If entropy is negative, it becomes less random. So we can imagine a situation, well, if heat is released and the reaction becomes more random, no matter what, we're on this red line. No matter what, entropy will it'll be right here. We're on the yellow line. It will always be spontaneous at all temperatures. If we have a negative delta H and a positive S, because it's negative T delta S, a positive delta S means delta G would increase further. So there'll be no situations where delta G would be 0. In those situations where delta G would be 0, so at different temperatures, it would just go from spontaneous to more spontaneous. You can imagine a situation where delta H is positive and delta S is negative, where it absorbs heat and becomes less random, where there's no temperature where it becomes spontaneous. It is always non-spontaneous. But there's some middling systems where the sign of both H and S are the same. When they're both negative, we have the situation, this light blue line. At low temperatures, it's spontaneous. At high temperatures, it's non-spontaneous. When you heat it up much, it won't go anymore. If you heat it up too much, it stops working. The reaction doesn't flow. You have one where they're both positive. At low temperatures, it doesn't work. But you heat it up high enough and suddenly it becomes spontaneous. And so there's a way we can calculate where this magic number is. What point will they both become spontaneous? Now, keep in mind, this high temperature, low temperature thing is all relative. Low temperature could be 500 degrees Celsius, but 500 doesn't sound too low, but in the scheme of things, yeah, it's not the sun. But we're saying if we want to find the temperature where it's spontaneous, we would say, at what point does it go from negative to positive? It goes from negative to positive right when delta G equals 0. Delta G equals 0, we can solve for temperature. So we add T delta S to the other side. We divide both sides by delta S, and we get H over S is equal to T. H over S is equal to T. Keep in mind, you have to turn kilojoules into joules or joules into kilojoules for this to work. But we can find the temperature in Kelvin through this. If both of these numbers are negative, you get a positive temperature. If both these numbers are positive, you get a positive temperature. But if one is positive and one is negative, you get a negative temperature. Because Kelvin can never go negative, you can never get a temperature where it doesn't work. Or you can never get a temperature where it does work. So only in these two middling situations will you be able to calculate that. So the equation we're going to look at is the Haber. They turn hydrogen and ammonia. What is the delta G at 25? And is there any temperature where this delta G might change? So let's look at our values. We have 3 hydrogen plus nitrogen goes to 2 ammonia. Looking at our values, delta H for hydrogen, nitrogen, and ammonia are 0046.49, and the delta S are 130.58, 191.5, and 192.5. Okay. Going to the DocCam. We're going to go to the DocCam and calculate our delta H, calculate our delta S. Delta H is really easy because half of these guys are stuff. So the delta H is just going to be negative 464 point. Let me go back real quick. Where did I? 46.49. Sorry. 46.4. So 46.49 times 2 minus 0 times 3 and 0 times 1. Essentially minus 0. So negative 46.49 times 2 is, the delta H is negative 92.98 kilojoules per mole. Delta S is going to be a little bit trickier. We have 192.5 times 2. All that minus 191.5 and 130.58 times 3. So 192.5 times 2, that's 191.5, and minus 130.58 times 3. We have a delta S value of negative 198.24. So this produces heat when it reacts, but it loses a lot of randomness when we go from 4 molecules of gas to 2 molecules of gas. So the first question is, what is your delta G at 25 degrees? We say take 292.98 minus 298 times negative 198.24 divided by 1,000. That gives us kilojoules per 1 joule. What kilojoules? 1,000 joules. So negative 92.98 plus 198.24. At this temperature, negative 33.9. Negative 33.9 kilojoules per mole. So this is spontaneous. Barely. It's spontaneous. Considering how much heat is produced, we've cut down the spontaneity down a lot, from negative 92 to negative 33. What temperature would it cease to be spontaneous? Well, the temperature of that case would be, remember, delta H over delta S. So we're going to say negative 92.98 times 1,000 joules per kilojoule. All that divided by negative 198.24. So 92980 divided by 198.24. The temperature which it would cease to be spontaneous is 469 Kelvin, which if we subtract out the 273, it's essentially 196 degrees Celsius. 196 degrees Celsius. Now, in terms of this, means if we allow it to heat up to 200 degrees or more, it's going to cease to work. The reaction is going to stop. And in fact, the hotter it gets, the slower it's going to go, the less likely it is to react. And with that in mind, this is why when they do this reaction, when they do the reaction that produces ammonia, they will chill it. They will actually cool this down. It's going to produce a lot of heat, and they will cool it down and thus force this to products. We talked about this briefly when we talked about Le Chatelier's principle. When we cool it down, it's removing a product, going to shift this towards products, and thus make this produce more ammonia. Now, we will see on occasion that a delta G and a delta G non-standard. What are the difference between the two? What does it mean to not be at standard state conditions? How do we treat that? What do we deal with? Well, delta G as standard is specifically defined as the free energy present when all compounds are at 1 molar or at 1 atmosphere. Now, if you look at this in terms of real world situation, very rarely concentrations all be at 1 molar. Very rarely will all concentrations be at 1 molar, especially if we're calculating K, equilibrium constant K. Very rarely will all products of reactants be at 1 molar. So thus, if you were to calculate K where everything is, if you calculate the equilibrium expression when everything is 1, that's not going to be equilibrium. That's going to be Q equals 1, but that's not actually equilibrium. Thus, it's going to suggest that if Q is not K, the reaction will keep proceeding until we get to Q equals K. So we can look at a reaction that says delta G standard, well, delta G non-standard equals delta G standard plus RT ln Q. R is our gas constant, 8.314. T is our temperature. And ln Q is the natural log, is a natural log of our reaction quotient. So in order to get the actual delta G to match up with our standard delta G, we have to factor in what are the actual products in reactant concentrations. So if concentration and pressures are at 1 atmosphere, if everything's at 1 and 1, then Q equals 1. If Q equals 1, natural log of Q equals 0. So if essentially everything is at standard state conditions, this equation simplifies just to state that delta G under those conditions is delta G standard. But essentially as Q approaches K, remember when we're at equilibrium, delta G non-standard goes to 0. When Q approaches K, delta G approaches 0. But remember, delta G standard will not change because it is an artificially defined point where everything is at 1 molar and 1 atmosphere. So if we know that delta G equals 0 at equilibrium, we have an equation that looks like this. 0 equals delta G standard plus RT ln K. Getting these to the opposite sides, we can get delta G standard equals negative RT ln K. It is possible to find out the equilibrium constant by knowing our delta G. It is possible to know our delta G by having our equilibrium constant. And in fact, you notice how there's temperature in here. You can factor in the temperature effect on our equilibrium constant K. So now it is possible to calculate delta G. Well, it's possible to calculate our equilibrium constant K from known values without actually having to do a chemical experiment. We don't actually have to put things into a vessel and then measure them at equilibrium to find our K, as long as we know our delta G values. Now, how do we get K by itself if we know delta G? First, we would divide both sides by negative RT. You would want to convert delta G into joules. And then you would take the inverse log of both sides to get K by itself. And that's where you get K equals E to the power of negative delta G over RT. But it's possible to find K from G or G from K. As I said, we would wrap this up together by the end. So, calculating delta G for this value, 3H2, we're going to go back to this. We had this, we calculated this. I'm going to go ahead and give us our delta G value again so we don't have to like do that math. But we just did this, 2NH3 at 25 degrees. If we have 3 atmospheres, 1 atmosphere, and 2 atmospheres, so 3 ATM, 1 ATM, and 2 ATM. What is our actual delta G for that situation? And I'm going to further ask, what is our K for that situation as we do this? So let's go to, so our delta G, what was it? Negative 33.9. Delta G non-standard is equal to delta G standard plus RT ln Q. Remember how we set up our Q? Our Q is equal to products over reactants. So NH3 squared H2 cubed N2 to the first. So real quick, what is our Q? Our Q value would be 2 squared over 3 cubed times 1. So 4 over 9. 4 over 9. Since we have our delta G is negative, delta G standard is negative 33.9 kilojoules per mole plus R, which is 8.314 joules per mole Kelvin. We have to multiply that by, convert that into kilojoules. We have to multiply that by our temperature at 25 degrees. It is 298 Kelvin. So that Kelvin and Kelvin cancel out. We multiply this by the natural log of 4 over 9. So let's go ahead and find this whole term. 8.314 divided by 1,000 times 298 times ln of 4 over 9. We do that. Negative 2.009. So when we add that to a negative 33.9, the delta G value is negative 35.9. So comparing this to the standard state, conditions, the 312 is actually farther from equilibrium than a 111. Now, taking this a step further, what is our K? What would our equilibrium constant actually be? It's obviously not 4 over 9. We need to produce more products. So delta G standard equals negative RT ln K. So we said this negative 33.9 equals negative 8.314 times 1 over 1,000 times, let's see, 298. ln K. So negative 33.9 divided by negative 8.314 times 1,000 divided by 298 will give us, we have positive 13.68 equals ln K. If I take the E to both sides, we have a big number. We have 8,75675 equals our K. So this is very much so product favored. That's a big number. But that would be how you could calculate for K at 298. If we were to refactor in, as temperature increases, K would decrease. If temperature increases, K would decrease, thus making the reaction less spontaneous and pushing this away. Okay. Now, and then I think one more, just practicing like this. Calculate delta G standard for the following equation, and then what is the equilibrium constant at 298? So this is the degradation of ozone by molecular oxygen. We kind of looked at this, just a pinch back in kinetics. So writing my values down, this guy is 230.1, that's positive 230. 163.4. These guys are not particularly stable. Which is why they have a positive delta G value. If I'm not mistaken, this is like our last slide. So delta G is equal to 0 times 2 minus 230.1 and 163.4. So our delta G is negative 393.5. 393.5 kilojoules per mole. You may have these situations. Negative 393.5. This is highly spontaneous. It's highly spontaneous. 98 by 1,000 ln K. Negative 393.5 times 1,000 divided by negative 8.314 divided by 298. You would get 158.8 equals ln K. And if you try to do this, you're actually going to come into a problem. You try to do the inverse log of this number, it becomes, well, okay, this one isn't too bad. Some numbers you may find are too big for your calculator to handle. This one, I guess, is not. I was thinking I gave you one that was. But sometimes you'll get a number that's actually too big for your calculator to handle, and it will go into overflow. It will not be able to calculate the exponent that large. When it gets to an exponent of 10, above 10 to the 99th power, I think it just gives up. But this one, oh, sorry, need to make sure it's on screen. You would get 9.47 10 to the 68th power. Not sure how clear that is, but 10 to the 68th power. So what does it say about this reaction? Holy cow, this reaction is very product favored. This reaction is very, very product favored. Ozone will naturally degrade really, really easily in the presence of monatomic oxygen. So this is a unstable situation just based on looking at delta G values. Of course, this will change with temperature, and rarely, if ever, I don't think the temperature up in the ozone layer is quite 298. So it will change a bit. But just to save ourselves a little bit of trouble, we're using the delta G values. Yeah. So that's where we're going to stop. We're going to stop a little bit early today because we end this chapter, and I don't really want to fuss around with the trying to get into achieve right now. So you have the test tonight. We will, on next Tuesday, we will start looking at this homework. We'll spend a little bit of time on this homework because this homework is starting to get a little bit more mathematically intensive. And I think we have plenty of time. We'll eventually, either middle of Tuesday or late Tuesday, we will start electrochemistry, which will be similar, but not quite the same, and end up around the same spot where we relate electrochemistry to spontaneity and electrochemistry to equilibrium again. And then continue on in that phase. So we have electrochemistry and spontaneity. Those are going to be the big things for test 4. Though we might, depending on how we're doing and how we're doing on the time, we will eventually go into nuclear chemistry, but I'm still up in the air whether I'm going to include that on test 4 or not. There might be 1 or 2 questions, but maybe not. With that in mind, I am going to go ahead and call it a little bit early. You can go and start studying if you haven't. So I will see you guys a little bit later. Have a good rest of the day, and I'll hopefully see you tonight.